You know, a session that we have spent on determinants. Essentially, you know, that was a collection of numbers placed in a square grid. Number of rows and number of columns were equal. And the output of that operation was a number. The output of that operation was a number. Now, we'll take a step back. We'll get into the rudiments of what is referred to as linear algebra, which is again a set of operations performed on a grid in general. Collection of numbers arranged in rows and columns. Collection of numbers arranged in rows and columns. The output of that operation is not a number. We refer to such a collection as a matrix. So, I talk of a matrix A. I talk of a matrix A whose representative element is like Aij, and this matrix A has m rows and n columns. It's referred to as m by n, m rows and n columns, and its representative element is Aij. Aij is an element of that collection belonging to the ith row and the jth column. The ith row and the jth column. This matrix has m rows and n columns. M rows and n columns. It is represented by this symbol. It's like the first row, first element, first row, second element, first row, third element, first row, nth element. Second row, first element, second row, second element, second row, third element, second row, nth element. Right? The first subscript represents the row number. The second subscript represents the column number. This is the first column. This is the second column. This is the third column. This is the nth column. Now going this way, the mth row. See, it has m rows. So mth row, first column. Mth row, second column. Mth row, third column. Mth row, nth column. This is just a collection of elements. The output of this is not a number. Right? We'll build an algebra around such a collection of numbers. We'll define operations for such a collection. Okay? Now, 1. If the number of rows is equal to number of columns in a matrix, this is a matrix m by n. It's a matrix m rows and n columns, m by n matrix, right? And if m equals n, it's a square matrix. If m equals n, it's a square matrix. If the number of rows equals number of columns, the matrix is called a square matrix. It's called a square matrix. If the matrix is like this, say for example, where this, for example, is a square matrix 4 by 4. 4 rows and 4 columns. It's a square matrix 4 rows and 4 columns, right? Columns are counted like this, rows are counted like this, right? In which all the diagonal elements, these are diagonal elements, the diagonal elements are II, are of the form II, right? This is A11, this element is A22, this element is A33, this element is A44, right? That's a designation of the diagonal elements in a matrix of this kind. It's a square matrix in which the diagonal elements AII represent the diagonal elements. Diagonal elements, and all elements are 0 and the diagonal elements are 1, right? This is called an identity matrix. It's called an identity matrix. This, for example, is an identity matrix of order 4. 4 rows and 4 columns. It's an identity matrix of order 4, I4. I could have had an identity matrix of order n. An identity matrix of order n would have n rows and n columns, and all the diagonal elements would be 0. All the diagonal elements would be 1. All the diagonal elements would be 1, and the rest of the elements would all be zeros. The rest of the elements would all be zeros. This is, for example, an identity matrix of order n. It's an identity matrix of order n. N rows and n columns. N rows and n columns, and all the diagonal elements are 1. In general, if all the diagonal elements are D, then we sometimes write that matrix as diagonal D1, D2, say Dn. These are the diagonal elements. The rest of the elements are 0. We sometimes write a matrix that only has diagonal non-zero elements, D1, D2, D3, and everything else is 0 in that matrix. That's a diagonal matrix. So a unit matrix or an identity matrix is a special case of a diagonal matrix where D1 equals D2 equals Dn equal to 1. An identity matrix or a unit matrix is a special case of a diagonal matrix. A diagonal matrix has all elements in its diagonals, in general D1, D2, Dn, say, and the rest of the elements as 0. That's a diagonal matrix that has only diagonal non-zero elements. Everything else is 0. Of course, in this diagonal elements, one or more could be 0 as well. Right? But for sure, the rest of the elements, except the diagonal elements, must be 0 in a diagonal matrix. Yes or no? And an identity matrix is only a special case of a diagonal matrix, where D1 equals D2 equals D3 equals Dn equal to 1. Right? Then we have what's called a row matrix. A row matrix has just one row. Say, a row matrix could be, for example, a matrix like this. It has one row and n columns. That's a row matrix. A11, first row, second column, first row, third column, first row, nth column. That's a row matrix. Collection of elements along a row. That's a row matrix. Then we have what's called a column matrix. A column matrix has just one column. So that's like this. In general, one column but n rows. Right? That's a column matrix. Right? Then we have what's called a null matrix. or a zero matrix? A null matrix or a zero matrix? A null matrix has all elements 0, has all elements 0, commonly designated as 0. This is not the value of the matrix. This is not the value. A matrix does not have a value. It's only a collection of elements, by the way. We can perform operations on that collection. We'll define algebraic operations on that collection of elements, right? So we have a null matrix which is like all elements 0. That's a null matrix. Yes or no? Can I wipe this off? Then for square matrices, we have another nomenclature, broad nomenclature. Let's say if I have a square matrix of order n, if I have a square matrix of order n, that means it's n rows and n columns. Order n means n rows and n columns, right? So we have like A11, A12, A1n, A21, A22, A2n, ANN. That's a square matrix of order n, n rows and n columns. N rows and n columns. Now, some square matrices could be such, where Aij equals Aji. That means the element in the ith row and the jth column will be the same as the element in the jth row and the ith column. Some square matrices will have this property. Aij is Aji. Element in the ith row and the jth column will be the same as the element in the jth row and the ith column. Square matrices that are commensurate with this property, are called symmetric matrices, These are symmetric matrices. That means A12 will be the same as A21, A13 will be the same as A31, and so on and so forth, right? These are symmetric matrices. If Aij is minus Aji, then that's called a skew symmetric matrix. That's called a skew symmetric matrix. If Aij is minus Aji, it's a skew symmetric matrix. Clear? Yes. We define symmetric and skew symmetric matrices only for square matrices. That's why I said, of square matrices, some of them would be symmetric, some of them could be skew symmetric, some of them would be neither symmetric nor skew symmetric, right? And in a skew symmetric matrix, put I equal to j, for example, as a special case, which will represent the diagonal elements. Diagonal elements are I equal to j, right? In skew symmetric matrices. So put j equal to I, so I have aii equals minus aii. Aii is minus aii. That means aii is 0. That means all the diagonal elements must be 0 in a skew symmetric matrix. All the diagonal elements must be 0 in a skew symmetric matrix. Yes or no? Right? Of course, let me not, although I could classify matrices in many more ways, but books will present that unnecessary redundant classification. But in terms of classification, this would suffice as of now. But then few little additions to that classification will be made as and when required, right? But now let's get into more of algebra of this collection of matrices. Again, I repeat, a matrix is not a number. It's only a collection of numbers, real or complex. Okay? It's not a number. The output of this operation, there is no operation. This is just an organized collection of numbers. That's all. Right? But then, even with a collection of numbers, you can perform operations. Say, I have a matrix A represented by Aij, and it's a m by n matrix, means mth row and m rows and n columns, m rows and n columns. This is a matrix A, and these are its representative elements, right? I varies from 1 to m, and j, which is the column number, varies from 1 to n, right? It's a m by n grid. And another matrix, m by n only, represented by Bij, that's also a m by n matrix. We say these are matrices of the same order, m by n. Order of the matrices, m by n. They are of the same order. So the elements here are like B11, B12, B13, B1, right? B1n, B21, B22, B23, B2n. Going this way, m rows and n columns, right? Now, two matrices of the same order, m by n, we could add those matrices. So when I say C is A plus B, then A plus B is an operation which is possible. A plus B is an operation which is possible only if both matrices are of the same order, m by n. Same order, m by n, only then you can perform this operation. Now, so if A and B are m by n, then their sum, which is C, will be, let's say, some Cij. That will also be of order m by n. That's also of order m by n. Now, the ijth element of C would be the ijth element of A plus ijth element of B. Such is the definition of the ijth element of C, which is obtained by the summation of A and B. I mean, if I have a matrix, say, A1, A2, A3, B1, B2, B3, this very clearly is a 2 row 3 column 2 by 3 matrix, and a 2 by 3 matrix can be added only to a 2 by 3 matrix, and say there is like, it's added to C1, C2, C3, D1, D2, D3. Then this element to be added to this element to be added to this element, this to this, and so on and so forth. Aij would be added only to Bij, right? So then this sum is, for example, A1 plus C1, A2 plus C2, A3 plus C3, B1 plus D1, B2 plus D2, B3 plus D3, right? Do you understand what I've done here, Arito? Right now? And this operation is commutative. A plus B is the same as B plus A. A plus B is the same as B plus A. It's commutative, right? This operation of addition is commutative. Also, if I add 3 matrices, say A plus B. Plus, of course, when I add matrices, they have to be of the same order. They must enjoy the same number of rows and columns. A plus B when added to C is the same as A when added to B plus C. This operation is, this is associative. This is associative. Yes or no? Right? Clear? Now, see, just like a vector, you know, it's a collection of numbers only. 2i plus 3j plus 5k. It's a collection. So you could have looked upon that as a row matrix 2 3 5. 2i 3j 5k 2 3 5. That could have been looked upon as a row matrix. It doesn't have a value. Its magnitude will have a value, but the vector per se has no value. But it's valuable. Right? So same with a matrix. It doesn't have a value. We'll perform operations on matrices that will produce values. That's a different thing. But the matrix per se is just a raw, benign collection of elements. Right? When I talk of a number, we'll call it a scalar. We'll call it a scalar k. Right? The matrix is like, loosely or strictly, I'll call it a vector. I'll call it a vector. Right? So, if I have a matrix A, and I multiply it with a scalar k, then it produces an output which would be a matrix B. It would produce an output which would be a matrix B, where k is a scalar. K is a scalar, right? Just like when you multiply a vector with a scalar, the output would be a vector. A matrix when multiplied with a scalar, the output would be another matrix, which is like, let's say, similar to a vector. And the ijth element of B would be k times ijth element of A. Which means, say if I have a matrix 1 2 3 5 1 1 2 3 9, suppose this is a matrix, and I have to multiply this matrix with 2, say for example. I have to multiply this matrix with 2. Then what happens is, every element of this matrix will get multiplied with 2, and the new matrix would be like a 2 4 6 10 2 2 4 6 18 would be the new matrix. So if I multiply A with k, then every element of A will get multiplied with k. This is what happens, right? Now, in general, let me go ahead and define multiplication of two matrices. When it came to multiplication of vectors, you know, the equivalent that we saw in terms of multiplication of vectors was dot product and cross product. Now, to get a little more general with things, we'll define multiplication of two matrices. And it's not like two matrices can always be multiplied. We will define restrictions on when they could be multiplied, right? So, if I have a matrix A, which is represented by, say, Aij is its representative element, and it has m rows and n columns. Okay? This matrix has m rows and n columns. Then it could only be multiplied with another matrix whose rows will be equal to number of columns of A. A could only be multiplied with another matrix B, where B has to be, let's say its representative element is Ij. it must be of the form n by p. That means the number of columns of A must be equal to number of rows of B, right? A and B, AB, which is multiplication of two matrices, AB, multiplication of two matrices, is defined only when number of columns of A equals number of rows of B. Number of columns of A equals number of rows of B. Only then the multiplication of two matrices A and B is defined. So if I have a matrix which is 2 by 3, it could only be multiplied with, let's say, a matrix which is 3 by something, say 3 by P. It can't be multiplied with a matrix other than a matrix of this form. Number of columns of this matrix must be equal to number of rows of this matrix. The order is important. AB is not the same as B. If AB is possible, it's not necessary that BA is also possible. Do you realize that? Say if this A is of 2 by 3 and B is of 3 by P. So A into B is possible because the number of columns of this is equal to number of rows of this. But if I say BA, hey, then the number of columns of this P is not necessarily equal to 2. Number of columns of this is not necessarily equal to 2. So even if AB is defined, BA may or may not be even defined. You know what I'm saying? If AB is defined, BA may or may not be even defined. Far from being equal to AB, far from being necessarily equal to AB. It may not even be defined. Right? The number of rows of the number of columns of the first matrix must be equal to number of rows of the second matrix. You know what I'm saying? And once they are commensurate with this condition, they could be multiplied. A could be multiplied with B. And we end up getting a matrix which is C. We end up getting a matrix which is C. We end up getting a matrix which is C. And the order of C would be M by P. I'll show you that. You'll realize that yourself. C would be M by P. If A is M by N, B is N by P, then C would be M by P. The product of A and B would be a matrix M by P. Now the question is, how does it work? How do I find the various elements of C, which is a matrix obtained by multiplying two matrices A and B, as long as they are commensurate with that multiplication? Say, I have a matrix A which is A11, A12, A1n, this is a matrix A which is like m rows and n columns. This is a matrix A which is m rows and n columns, right? And this I want to multiply with a matrix B. B must be n rows and p columns. N rows and p columns. The number of rows of B going this way must be equal to number of columns of A, right? Now B is, say, n rows and p columns. So B is like B11, B12, B13, B1p, right? P columns. Do you realize that? It has P columns. And in general, the jth column of this is like B1J, B2J, jth column. I'm talking about the jth column, right? The second number represents the column number, right? B1J, B2J, BNJ, right? Yes or no? That's a matrix B. Do you realize that the number of columns of this is equal to number of rows of this n? This is a M by N matrix. This is a N by P matrix. Yes or no? And they are conformable towards multiplication. Number of columns of this is equal to number of rows of this, each equal to N. The product would be C, which would be a matrix M by P. It will have M rows and P columns. You know what I'm saying? Now the question is, this is the matrix C. This is the matrix C. Okay. Now, C is a matrix which is like Cij. It has element Cij. And it's going to be M by P, M rows and P columns, M rows and P columns. Let me call this the ith row. I'll tell you why. Let me say this is the ith row of this. AI1, AI2, AIN, right? AI. This is the ith row of A. And this is the jth column of B. This is the jth column of B. This is the ith row of A. And that's the jth column of B. That's the jth column of B. Right? Now, how do I obtain Cij, the ijth, the member belonging to the ith row and the jth column of C? C is the product of A and B. So, when I have to obtain the ijth element of C, the product, right? That means I am obtaining the ijth element of AB. Essentially, what am I obtaining? The ijth element of AB. This is what Cij is, isn't it? Ijth element of AB. The product AB. For that, we populate two things. We take the ith row of A and the jth column of B. This is the ith row of A and this is the jth column of B. This is the ith row of A and this is the jth column of B. Now, what represents the ith row of A? Ith row of A is represented as, say, AIK kind of a thing, where K varies from 1 to N. Yes or no? Ith row is AIK, where K could be 1, K could be 2, K could be 3, K could be N. That's a ith row in general, where K is allowed to vary. K is allowed to vary. Right? K varies from 1 to N. And what represents the jth column of B? BKJ. 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 Yes or no? BKJ. To obtain the ijth element of AB, what is it that I do? I take members in the ith row of A, which is this. I take members in the jth column of B. And then I multiply AI1 with B1J and add to it AI2 into B2J, AIN into BNJ. You know what I'm saying? I perform this the following operation. To obtain Cij, I take the ith row of A and the jth column of B. Then I multiply this with this, to which I add this into this into this, and this into this. This is what I do. That means essentially I'm taking the corresponding members, adding them up. K runs from 1 to n. K runs from 1 to n. That's an ordered multiplication. That's an ordered multiplication. That's why the number of columns here should have been equal to the number of rows there. Yes or no? That's when I could have done a 1-to-1 multiplication. Yes or no? Only when the number of columns here in the first equals number of rows here. That's when this operation would have been possible. Yes or no? And this with this, that is like this into this plus this into this, etc. That's called an inner product. Inner product of the ith row of A and the jth column of B. It's called an inner product of the ith row of A and jth column of B. What is this? This is an inner product of the ith row of A and the jth column of B. Cij is what? Cij is obtained by taking the inner product of the ith row of A and jth column of B. Ith row of A and jth column of B. Yes or no? That's Cij. So, you understand how this summation got formed? Right? All of you understand how this summation got formed? Yes or no? Right? Now, which is like, every time I'm not going to write a summation notation, I'm going to be a little more laymanish in my expression. I'm going to say, okay, this is like inner product of ith row of A into jth column of B. Ith row of A into jth column of B. That's this inner product. This is the ith row of A and jth column of B. That's called an inner product. This into this plus this into this plus this into this, and so on and so forth. Yes or no? Right? Huh? All's good, right? No issues with this, right? Now, say there is a matrix A which is two by three. There is a, say, 2 rows and 3 columns. So this matrix is, say, A1, A2, A3, B1, B2, B3. That's a matrix A, 2 rows and 3 columns. And say there is a matrix B, which is like 3 by 1. 3 rows and 1 column. 3 rows and 1 column. This is 3 rows and 1 column. Yes or no? Can I multiply these two matrices? Yes, because the number of columns of A equals number of rows of. So AB is possible, but is BA possible? No, BA is not possible. BA is not possible. A into B is possible. So if I have to multiply these matrices AB, then that will give me another matrix. And so what would I do? I'll take this row and then this column, right? I'll have an element A1 C1, A2 C2, A3 C3, isn't it? I'll take The C11 would be first row of this and first column of this, right? So that's going to give me like a A1C1 plus A2C2 plus A3C3, which is the inner product of this and this, right? Then I'll go to the second row of this and inner product of this and this. So that's going to give me like a B1C1 plus B2C2 plus B3C3. That's the output of this multiplication, yes or no? That's the output of this multiplication. Do you see that it's what's the order of this matrix? How many rows? 2 rows. And how many columns? 1 column. So do you realize that this AB is a 2 row by 1 column, which is what we expected, isn't it? If I multiply m by n with n by p, I get a matrix which is m by p, 2 by 1. Is it not a 2 by 1 matrix, which is what we expected out of this multiplication? Yes or no? Right? Fairly simple, huh? But again, AB exists here, BA doesn't even exist. BA doesn't even exist. Now, if it's possible to multiply A and B, then 1 lambda times AB, where lambda is a scalar. I'm assuming this operation AB is possible and lambda is a scalar. Then I claim that this will be the same as lambda A into B. And also it's the same as A into lambda B. That's an easy to see property. You'll be able to establish it yourself. 2. In general, AB is not equal to BA in general. If it happens, it's only a special case. But in general, multiplication is non-commutative, In general, non-commutative. 3. ABC, I'm assuming this operation is defined. That's the same as A into BC, or which is the same as AB into C. This property is associative. Associative property, assuming all these operations are defined based on multiplication of matrices. It's an associative property. Commutative, not necessarily true, but associative, true. A into BC, ABC is like A into BC, which is the same as AB into C. A into B plus C. Hey, assuming B plus C, B and C can be added. If they are matrices of the same order, they could be added. And then A into B plus C is a possible multiplication. B plus C would be a matrix which could be multiplied with the matrix A. This is like AB plus AC. This property is distributive. Distributive property, right? This is associative. Distributive. And similarly, A plus B into C will be the same as AC plus BC. AC plus BC. Also distributive, right? Huh? All distributive laws. All distributed laws. If AB is a null matrix, its value is not 0. It means it's a null matrix. All elements of the product AB is 0. If A into B produces a null matrix, 0. This doesn't mean the value of the matrix. It only means that all elements of the matrix are 0. If AB is a null matrix, it doesn't mean that A is 0 or B is 0 or B is 0. Does not mean A 0 or B 0 or BA 0. In fact, BA may not even be defined. If AB is a null matrix, doesn't mean that A has to be a null matrix or B has to be a null matrix or BA has to be a null matrix. Maybe it's not even defined. Right? Got me? Yes or no? Can I wipe this off? And two matrices would be equal. One, they have to be of the same order, m by n. Two, their corresponding elements must be equal. That's when two matrices are equal. Two matrices would be equal if their corresponding elements are equal. A matrix A equals matrix B. If a matrix A is equal to matrix B, it means Aij must be equal to Bij. Right? So far, so good. Then we have an operation. We have another operation called the transpose of a matrix. We have an operation called the transpose of a matrix. Denoted by the symbol T. So what essentially transpose means is, suppose I have suppose this is a matrix A. Suppose this is a matrix A. When I say I'm going to transpose this matrix, I convert rows into columns and columns into rows. Right? The first column will become the first row. So A transpose would be like A, D, G, J. The first column would have become the first row. The second column will become the second row. The third column will become the third row. That's a transpose of a matrix. Right? So if this is A, this is A transpose. Very clearly, this A is a matrix which is 4 rows and 3 columns. So it's a 4 by 3 matrix. It's a 4 by 3 matrix, and its transpose is now 3 rows but 4 columns. 3 rows but 4 columns. Hey, one more quick thing on multiplication of square matrices. Just make a note of it. If In is a square matrix of order n, if In is a identity matrix means what? Diagonal elements 1, everything else 0. That's an identity matrix or a unit matrix, right? And if A is a matrix of order n, then A into In will be the same as In into A will be the same as A. You multiply a matrix of order n with an identity matrix of order n, you will get the same matrix A. Or you interchange this operation, then also the same output A would be produced. Okay, so if A is 4 by 3, A transpose would be 3 by 4. Would be 3 by 4. Also, do you see that in a transpose operation, this element that was A12, element belonging to the first row and second column is now the element belonging to the second row and the first column. Yes or no? Right? Yes or no? Element belonging to the third row and first column is equal to element belonging to the first row and third column. Yes or no? So interchanging rows into columns and columns into rows. So if A is a matrix, and B is a matrix which is transpose of A, this is B, which is transpose of A, then A21, this is A21, this is first row, second column, right? A21, second row, first column, right? If A is a matrix and B is obtained by transposing A, then the ijth element of A will be jith element of B. The ijth element of a matrix A will be jith element of its transpose. Right? The ijth element of a matrix will be jith element of its transpose. Isn't it? Yes or no? So transpose is like converting rows into columns and columns into rows. So far so good, right? Now, few very basic properties of transpose. One, if you transpose a matrix A, and then again transpose it, you get A back, isn't it? You have converted rows into columns and columns into rows, and then another transpose would have restored the original matrix A. So A transpose will always be A. And perform this transpose an even number of times, you will restore the matrix. Yes or no? If K is a scalar, and it's multiplied with the matrix A, K is a scalar and is multiplied with the matrix A, then Ka transpose will be the same as K times A transpose, Then A plus minus B transpose, assuming A could be added and subtracted with B, that's the same as A transpose plus minus B transpose. The transpose of A plus B would be transpose of A plus transpose of B. The transpose of A minus B would be transpose of A minus transpose of B. Right? Clear? Now, A, B, it's possible to multiply A and B, say. Now this is an important property which will require some attention. If AB is transposed, I hope all of you are there with me on this, and I'm not moving too fast with things, right? If AB is transposed, then that will give me B transpose into A transpose. That will give me B transpose into A transpose. Hey, when I transpose a vector, when I transpose a matrix, the ith row will become the jth column. Ith row will become the jth column. Order changes, right? I'm sorry, the ith row becomes the ith column in a transpose. When I transpose, whatever was the ith row will now become the ith column. And whatever was the ith column will become the ith row. Row and columns will get interchanged in a transpose. This is what happens. Yes or no? Now, this is an important property. AB transpose is B transpose into A transpose. Now, I will establish this property. The rest were like pretty easy to check. You'll be able to do it independently. But this one, let me spend a while on this property. AB transpose is B transpose into A transpose. Now, if I can show that the ijth element of this is the same as ijth element of this, then the problem is solved, isn't it? In general, if I can establish that the ijth element of AB transpose is the same as ijth element of B transpose into A transpose, then this property gets established, right? Now, ijth element of AB transpose the ijth element of AB transpose would be the jith element of AB. The ijth element of AB transpose, I claim, will be the same as the jith element of AB, isn't it? This is what transpose does, right? Yes or no? Now, how does one obtain the jith element of this product? I take the inner product of jth row of A and ith column of B. This is what I do, isn't it? How do I find the jith element of a product? I take the jth row of the first and the ith column of the second, and I carry out an inner product, right? This will be the inner product. This will be the inner product of jth row of A I'll take and ith column of B I'll take, right? With ith column of B. Jth row with ith column, yes or no? Hey, jth row of A is the same as jth column of A transpose. This is what transposition would have done, right? Jth row of A would be like jth column of A transpose. Ith column of B will be like the ith row of B transpose. Yes or no? Right now? So, this I can write as inner product of ith row of B transpose, ith row of B transpose into jth column of A transpose. Yes or no? Right? So, this is inner product of this one, which is like ith row of B transpose into, B transpose is a matrix, right, into jth column of A transpose. Yes or no? Yes or no? So essentially in this inner product, I'm taking the ith row of B transpose and I'm taking the jth column of A transpose. Yes or no? Which is the ijth element, of B transpose into A transpose, isn't it? How do you find the ijth element of B transpose A transpose? You take the ith inner product of ith row of B transpose and jth column of A transpose. Ith row of B transpose into jth column of A transpose. This inner product will give me ijth element of B transpose into A transpose. Yes or no? Are you all there with me? Which means ijth element of AB transpose is the same as ijth element of B transpose into A transpose. Yes or no? So which means AB transpose therefore must be the same as B transpose into A transpose. Yes or no? Clear? Important property. So, if AB is defined, BA may or may not be defined, but B transpose into A transpose has to be defined. Yes or no? If AB is defined, then BA may or may not be defined, but B transpose A transpose has to be defined. Very easy to see. See, if A is like a M by N, B has to be like a N by P. Yes or no? Now B transpose would be like a P by N. B transpose would be P by N. Rows have got converted into columns and columns into rows. And A transpose would be like a N by M. So this multiplication is valid because the number of columns of B transpose is equal to number of rows of A transpose. So this multiplication is confirmable. Yes or no? So AB transpose is B transpose into A transpose. Very commonly used property. Very commonly used property. Right? Can I wipe this off? Now, if A is a square matrix, order n, right? A is a square matrix of order n. If A is a square matrix of order n, n by n, n rows and n columns. And if A transpose is equal to A, if A transpose is equal to A, then A is called a symmetric matrix. A is called a symmetric matrix. That means converting rows into columns and columns into rows. If no change is perceived in the matrix, then the matrix is called a symmetric matrix. That can happen. That can happen only if the ijth element is the same as jith element. That can happen only if the ijth element of A is the same as jith element of A. Because when I transpose, the ijth element becomes the jith element. Isn't it? So no change should be perceived when the transposition is carried out. That can happen only if the ijth element is the same as jith element. Then the matrix will be the same as its transpose, and the matrix would be referred to as a symmetric matrix. Confused? If A transpose is minus A, that means if the ijth element of A is minus a jith element of A, then the matrix is called a skew symmetric matrix. And that can happen. So in a skew symmetric matrix, now what happens to the diagonal elements? The diagonal elements will have I equal to j. That means aii will be minus aii. That means aii will be 0. The diagonal elements will be 0 in a skew symmetric matrix. The diagonal elements will all be 0 in a skew symmetric matrix. Now in general, for transposition, let me also tell you, if I have p, q, r, s, this whole thing, this multiplication is valid, let's say, and I transpose this, then this transposition, no matter how many matrices I have, that's going to be S transpose, R transpose, Q transpose, P transpose. Now, every square matrix can be expressed uniquely as a sum of a symmetric and skew symmetric matrix. I'll write down. Can I wipe this off? Every matrix, square matrix, every square matrix can be uniquely represented square matrix can be uniquely represented as a sum of a symmetric and skew symmetric matrix. Every square matrix can be uniquely represented as a sum of a symmetric and skew symmetric matrix. Let's see how. So let's say A is a square matrix. I want to write this as a sum of P, which is a symmetric matrix, and Q, which is a skew symmetric matrix. P is a symmetric matrix, Q is a skew symmetric matrix. How do I find P and Q, say? How do I find P and Q? Given A, I want to write A uniquely as a sum of a symmetric and a skew symmetric matrix. Symmetric and skew symmetric matrix. This is what I want to do, right? Now, if I know A, I can find its transpose. A transpose would be P plus Q transposed. Yes or no? A transpose would be P plus Q transpose, which is like from properties of transpose, P transpose plus Q transpose. Yes or no? Hey, but P is symmetric, so P transpose must be the same as P, and Q transpose must be the same as minus Q, because Q is skew symmetric. Yes or no? So A transpose becomes P minus Q, right? A is P plus Q and A transpose is P minus Q. Yes or no? Now if I add, P then becomes half of P A plus A transpose. Yes or no? If I add, 2P becomes A plus A transpose. P would be A plus A transpose by 2. What is Q? Q is half of A minus A transpose. So P and Q unique, isn't it? P is symmetric, whereas Q is skew symmetric. Right? Can I wipe this off? Every square matrix can be delivered with P and Q, where P is a symmetric matrix, Q is a skew symmetric matrix. Clear? So far so good. Now suppose U and V are two symmetric matrices. Are two symmetric matrices. Then I claim that U, V, U will also be a symmetric matrix. If U and V are symmetric matrices, U, V, U will be a symmetric matrix, I claim. Now, when would I know that UVU is a symmetric matrix? If its transpose is equal to the matrix itself. If the transpose of this matrix turns out to be UVU, then the matrix is a symmetric matrix. Now, from this property of transpose, this is like U transpose into V transpose into U transpose. Yes or no? Hey, but U is symmetric, V is symmetric. So U transpose will be U, V transpose will be V. So this is like a U, V, U. Thus, U, V, U would be a symmetric matrix. U, V, U would be a symmetric matrix. Yes or no? Right? And in any order, it does not matter because of the associative property will hold good. Right? Also, if say A and B are symmetric matrices, then AB will be symmetric. The product AB will be symmetric if AB equals BA. I claim that if A and B are symmetric matrices, then the product AB will be symmetric. The product AB will be symmetric if AB is BA. खेनी चाहिए थोड़ा? हाँ, वो भी तो ओवर हैंगिंग है. नहीं समझे? So if A and B are symmetric matrices, then AB will be symmetric if AB is BA. Let's see how. Okay. Okay. Now, when would AB be symmetric? If AB transpose is AB, right? Now, if I can show that AB transpose is AB, then AB will be symmetric. But AB transpose anyways is B transpose into A transpose. Property that we learned. But B transpose is B. Why? Because B is symmetric. A transpose is A because A is symmetric. So this is like BA. But I want AB to be symmetric. So AB transpose must be the same as AB. AB transpose must be the same as AB. That means if BA equals AB, then AB will be symmetric. If BA equals AB, then AB will be symmetric given that A and B are symmetric matrices. Given that A and B are symmetric matrices. Yes or no? Yes. See, AB transpose is B transpose into A transpose, right? But B transpose is B. A transpose is A. But if AB has to be symmetric, then AB transpose must be equal to AB. Because isn't it? I want AB to be symmetric. So AB transpose must also be equal to AB. So that gives me BA equals AB. That means if BA equals AB, then AB will also be symmetric. Given that A and B are symmetric matrices. Given that A and B are symmetric matrices. How about it? All's good? If A and B are symmetric, then the matrix P, which is AB plus BA, will also be symmetric, I claim. If A and B are symmetric matrices, then the matrix P, which is AB plus BA, will also be a symmetric matrix. Let's see how. Now, P transpose. I want to show that P is symmetric. P transpose is like AB plus BA transpose. Right? Which is like AB transpose plus BA transpose. Right? Which is like B transpose into A transpose plus A transpose into B transpose. Yes or no? But B transpose is B. Why? Because B is symmetric. A transpose is A because A is symmetric. So this is like BA plus AB. BA plus AB. Which is the same as P. Which is the same as P. Which is AB plus BA, which was P. So P transpose is the same as P. P therefore must be symmetric. Right? So if A and B are symmetric matrices, then AB plus BA will also be a symmetric matrix. No confusion? Also, Q, which is I claim AB minus BA, will be skew symmetric. I claim if A and B are symmetric matrices, then AB minus BA will be a skew symmetric matrix. Right? Let's see how. Same way. What is Q transpose? Q transpose is like AB minus BA transpose. Hey, some authors, instead of writing A transpose, they write A dashed. So don't get confused. I just want to be unequivocal about this, so I write T. But some people choose to write A prime, which also means A transpose. So that's okay. So then, Q transpose is AB minus BA transpose, which is like AB transpose minus BA transpose, right? Which is B transpose into A transpose minus A transpose into B transpose, right? B transpose is B, A transpose is A. So this is like BA minus AB, which is minus of AB minus BA, which is minus of Q. So Q must be Q symmetric because Q transpose is minus Q. Yes or no? Shall I proceed? Now, so you know this foundation of linear algebra, let me tell you, would go a long way. You know, extensions of this, more and more of linear algebra, this is just the beginning, but more and more of linear algebra would set you up for AI. AI uses linear algebra as a very, very powerful tool. Now, say if A is a square matrix of order n, if A is a square matrix of order n, now for a collection of elements in a square grid, we've defined an operation whose output is a number, that's determinant A, right? For a collection of elements in a square grid, we've defined an operation which is determinant of A, that's a number, that's a scalar. Determinant of A is K, a scalar, that's a number, right? And henceforth, so in context of matrices, this symbolism would actually mean determinant of A. This would mean determinant of the matrix A, not mod A. It would mean determinant of the matrix A, which we earlier designated as delta. From now on, we'll call it determinant A with two parallel bars, right? This would mean determinant of the square matrix A. This would be a scalar. The matrix is not a scalar, but its determinant is a scalar if it exists. It will exist only for square matrices, right? Of A. For every square matrix, you can define the matrix of its cofactors. Remember that? Right? F, say, is the matrix of its cofactors. F is the matrix of cofactors of A. Right? We've done that before. You have not forgotten, I'm assuming. Right? Now we define another operation pertinent to linear algebra, which is called adjoint of A. of the matrix A, which is written as ADGA, adjoint of the matrix A, which is also a matrix, If A is a matrix, adjoint of A is also a matrix. But what's that matrix? It's the transpose of F. It's defined as the transpose of F. Transpose of the cofactors of A. A is a matrix. What is adjoint of A? Constitute F, which is the matrix of cofactors of A, and transpose that matrix. Then this matrix is defined as the adjoint of A. Matrix of cofactors transposed. Matrix of cofactors transposed. That's adjoint of A. That's the definition. Now, this operation, multiplying a matrix A, a square matrix A, with adjoint of A, What is adjoint of A? Transpose of cofactors of A. Transpose of cofactors of A, that's adjoint of A. So these are two. And if A is a square matrix of order n, F will also be a square matrix of order n, isn't it? Its transpose will also be a square matrix of order n. So it's good enough for multiplication, right? Now, ijth element of this multiplication. Ijth element of this multiplication. Let us see what that is. Ijth element of this multiplication. How do you handle this? You take the inner product of ith row of A and jth column of adjoint of A, and jth column of adjoint of A. Yes or no? That's what you do, right? Inner product of ith row of A and jth column of adjoint A. Jth column of adjoint A means F transpose. Adjoint A is actually F transpose. Matrix of cofactors of A transpose, that's adjoint A, right? Ith row of A into jth column of adjoint of A. Adjoint of A is matrix of cofactors transposed, right? Now, jth column of F transpose, is it not the same as jth row of F? Jth column of F transpose is actually the jth row of F. Right? So this is inner product of ith row of A into jth row of F. F is what? The matrix of cofactors of A. Matrix of cofactors of A, right? Now, if I take, so there are two possibilities. I can be equal to J or I is not equal to J, right? Do you realize when I is J, that means I take the ith row of A and the same row of its cofactors, then it will give me determinant A. That inner product will give me determinant of A, right? When I is J, I take the ith row of A and the same row of its cofactors, right? Then I get determinant A. Yes or no? When I is J. But if I is not J. That means, you know, if I take some row of A, but some other row of its cofactors, then the inner product is 0. Right? That means when I is not J, then this inner product is shunya. Yes or no? Right? Clear now? Now, A adjoint A is a matrix. A adjoint A is a matrix whose diagonal elements I equal to J are diagonal elements is a number equal to determinant A. A adjoint A is a matrix. A adjoint A is a matrix, right? Whose diagonal elements I equal to J is a diagonal element is equal to a number equal to the determinant of A. And the rest other elements are 0. So that means A adjoint A is a diagonal matrix whose diagonal elements are equal to determinant A, yes or no? Right? So A adjoint A is a matrix like this. Is a matrix like this. All diagonal elements are this diagonal matrix and everything else is 0. Everything else is 0. Right? That's A adjoint A. All diagonal elements are determinant of A and the rest of the elements are all zeros. That's A adjoint A. Yes or no? Now, is that okay? Where this is a scalar. Determinant A is a K. A scalar. Right? Now, can I remove this portion? Just this portion? This is like the scalar delta A coming out, right, into this determinant, into this matrix 1 1 1 0 0 0, isn't it? Which is a unit matrix IN, which is a unit matrix IN, yes or no? So this turns out to be determinant A, which is a scalar K into IN, yes or no? IN is a matrix, will give me the matrix part of A adjoint A, and this will give me the scalar part of A adjoint A. This is a unit matrix, identity matrix into a scalar, All the diagonal elements of this would be determinant A. Everything else will be 0. So, A adjoint A, very important result, very commonly used, is going to be determinant A into the unit matrix of the same order as A. A is a matrix of order n, IN is a unit matrix of order n. IN is a unit matrix of order n. So A adjoint A is determinant A into IN. This essentially would be a matrix whose diagonal entities are determinant A, determinant A, determinant A, everything else will be 0. When I multiply this with IN would be diagonal elements 1 1 1, everything else 0. This you might want to independently prove. You take the other way around, adjoint A into A, which is the same as adjoint A into A. That will also be determinant A into I. You would want to establish this second part yourself. Adjoint A into A will also be determinant A into IN. Very, very powerful tool, very commonly used. I do not know if you've had, some of you might have had matrices in school. I think ICSE had, but CBSE also no. Okay. Oh, division. When did you divide matrices? That would be news. Okay. Right? Now, switch off, switch off the AC. Yeah. Now, adjoint of AB, A and B, let's say, are two square matrices of order n. Adjoint AB is adjoint B into adjoint A. Adjoint AB is adjoint B into adjoint A. Hmm? Let's establish this. Now, let me look at this AB adjoint AB. Just look at this. AB adjoint AB. A matrix adjoint of that matrix. What is that? Determinant of that matrix into a unit matrix of order n, right? So this is a matrix into adjoint of that matrix. A matrix into adjoint of that matrix would be determinant of that matrix into a unit matrix of the same order. So can I say this is determinant AB into a unit matrix of the same order In? Can I say this? So AB adjoint AB is this, determinant of AB into unit matrix identity. It's also called an identity matrix In. Now let me look at AB into this. Let me look at AB into this. Associative property. So I can carry out the multiplication by putting parentheses wherever I want, right? You realize what I'm doing? I'm doing AB into adjoint B into adjoint A. Now B into adjoint B, a matrix into adjoint of that matrix, is what? Determinant of that matrix into a unit matrix. A into determinant of B into a unit matrix of the same order as B into adjoint A. Yes or no? See, this is a scalar. It can easily wriggle out of this mess. Determinant B is a number. It can wriggle out of this mess, right? In is a unit matrix, identity matrix. When it's multiplied with the adjoint of A, it will give me adjoint of A. If a unit matrix is multiplied with a matrix of the same order, the output would be the same matrix. So when In is multiplied with adjoint A, it will give me adjoint A. Yes or no? And this, let me allow it to fall out. Determinant B, it's a scalar, it will come out into A. In adjoint A is adjoint A. In into adjoint A is adjoint A. But A adjoint A is determinant A into a unit matrix. Determinant B into determinant A is the same as determinant BA or the same as determinant AB. Right now? Same as determinant AB. That's a property we read in determinants into In. Hey, AB adjoint AB is determinant AB In. AB adjoint B into adjoint A is also determinant AB into In. Same? So these two must be equal. Now, one thing, it will require more discussion, but if I said PQ is PR, if P into Q is P into R, and if P, see, a matrix is called non-singular. A matrix, square matrix is called non-singular. A is a non-singular matrix if determinant of A is not 0. Is singular if the determinant of a matrix is 0, it's called a singular matrix. But if the determinant of that matrix is non-zero, it's a non-singular matrix. Another terminology, jargon that is commonly used. If P is non-singular, that means if determinant P is not 0. For square matrices, if determinant P is not 0, I can say that Q must be equal to R. I can say that Q must be equal to R. So, if this is equal to this, PQ is PR, PQ is PR, so Q must be equal to R. So, can I not say that Q equal to R? That means adjoint AB is adjoint B into adjoint A. I'm saying if P into Q is P into R and P is non-singular, I'll be able to, I've not established this, then I can say that Q must be equal to R if P is non-singular. I've not proved this result. It requires a proof. So, it is not like you can cancel two matrices from both sides. Never perform. Because they're not numbers that you can cancel. They're not numbers that you can cancel, right? So don't cancel matrices like this. That will be sinful. But Q equal to R requires a formal proof. But wait till I have not yet taught a concept which will enable me to prove this. So, but as of now, take it from me. P has to be non-singular. Sorry? Yes. See, if A is a square matrix, all these I'm talking of square matrices. A and B are square matrices of the same order. If they are square matrices but of different orders, they can't be multiplied. Hai na? A 3 by 3 matrix can't be multiplied with a 2 by 2 matrix. So if two square matrices are conformable towards multiplication, they have to be of the same order. So it brings us to another very commonly used result. Adjoint AB is adjoint B into adjoint A. Now, can I remove the clutter from here? So far, so good. Hey, if I have a diagonal matrix of order n, say this is a diagonal matrix of order n, all other elements are zeros. Huh? This is a diagonal matrix, say A of order n. Then the determinant of A will simply be d1, d2, dn will be determinant A. If A is a diagonal matrix, then the determinant of that matrix would be the product of the members of the diagonal. Okay. A is a square matrix of order n. Look at A adjoint A. Look at A adjoint A, which I said is determinant A into In. If these two are equal to this, if this is equal to this is just a matrix. This is not a number. This is just a matrix. This is also a matrix whose diagonal elements are determinant A. Whose diagonal elements are, it's a diagonal matrix, determinant A, etc. Right? Now, let me take the determinant of both sides. Now, determinant of AB would be determinant of A into determinant of B. That property. So, this is like determinant of A into determinant of adjoint of A. That's the left hand side. Now, this is a matrix whose diagonal elements are determinant A, determinant A, determinant A. Everything else is 0. So, the determinant of this matrix would be determinant A to power n. No? No? I'll repeat. See, determinant A in is like determinant A in would be like determinant A, determinant A, determinant A. That's determinant A in. Right? What will be the value of this, value of the determinant of this? What will be the value of the determinant of this? This, which is determinant A to power n? Yes or no? So, determinant of this matrix would be determinant A to power n. And if determinant of, if A is non-singular, hey, this is just a number. Now, both sides are numbers. Because we are talking of determinants, right? And if A is non-singular, that means determinant A is not 0, then I can divide by determinant A throughout. If A is non-singular, right? Then this gives me determinant of adjoint of A is determinant A to power n minus 1. This is a number, this is a number, this is a number, but this is not 0. Why is this not 0? Because A is non-singular. So can I not divide by determinant A? Determinant A is a number, that's not a matrix, it's just a number. No. So when I divide, then this becomes to power n minus 1. So determinant of adjoint of A is determinant A to power n minus 1. That means determinant adjoint of A means transpose of cofactors of A is determinant A to power n minus 1. N is the order of the matrix A, right? But determinant of transpose is the same as determinant of F. See, if you take a matrix and it's transpose, you'll get the same value of the determinant, isn't it? If you have a matrix and you transpose it, the value of the determinant will not change. By converting rows into columns and columns into rows, the value of the determinant remains unaltered. Nahi samjhe? Now, F transpose. The determinant of F transpose is the same as determinant of F. Where what is F? F is the matrix of cofactors of A. That means determinant of the cofactors of A is determinant of A to power n minus 1. Remember, we established this result for a 3 by 3 determinant. Determinant of the cofactors turned out to be determinant A squared. Remember that? For a 3 by 3 matrix? In general, for a matrix of order n. So that's a special case of this result. Determinant of the cofactors of a square matrix would be determinant of the matrix to power n minus 1, wherein n is the order of the matrix. N is the order of the matrix. You know what I'm saying? Another trivia. So far so good. I claim adjoint of A transposed, you should be able to establish this yourself, is the same as adjoint of A transpose. Adjoint of A transposed is the same as adjoint of A transpose. You got to be thinking about it independently. Regulation result. Now, if A is symmetric, then A transpose will be equal to A. If A is symmetric, A transpose will be equal to A. Yes or no? Then adjoint of A transpose will be the same as adjoint of A, if A, right? If A is symmetric. But if adjoint of A transpose is adjoint of A, it means adjoint A must be symmetric. It means adjoint A is symmetric. If adjoint of A transpose is the same as adjoint A, then adjoint A must be symmetric. That means if A is a symmetric matrix, then adjoint A will also be symmetric. If A is a symmetric matrix, then adjoint A will also be symmetric. And this has nothing to do with whether A is symmetric or not. This is cardinal. Adjoint of A transpose is adjoint of A transpose is true for all square matrices A. But if A is symmetric, then adjoint A will also be symmetric. You want me to repeat this? See, this result I want you to prove yourself. Okay. Now I'm claiming that if A is symmetric, adjoint A will also be symmetric. Now, adjoint A transpose is adjoint of A transpose, which anyways is always true. But if A is symmetric, A transpose will be equal to A. Right? And then if the transpose of this matrix is the same as this matrix, then this matrix must be a symmetric matrix. Adjoint A must be a symmetric matrix. So if A is a symmetric matrix, adjoint A must also be symmetric. Right?